Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! The Milky Way is an enigmatic feature in the night sky. There's a glow to it and bumps and swirls to it. There's a river of stars banded with a long black strip. It can be seen from the northern and southern hemisphere, so it's not surprising that different cultures from around the world have stories describing or explaining it. These stories and many others can be easily looked up on a Wikipedia page about it, and here's a sampling of them. Please pardon my pronunciation. So the Greek name for the Milky Way is Galaxias, and it's derived from the word milk. The deal is that when Hercules was a baby, Zeus, who was Hercules' father, decided to let him suckle on Hera's milk. Now, Hera wasn't Hercules' mother. She was Zeus's wife. Okay, so when she figured out what was going on, she punted the baby, and the resulting spurting milk became the Milky Way. The Kaurna Aboriginal people from South Australia see the Milky Way as a river in the sky world. They say the dark patches mark dwelling places of a dangerous creature called the Yura. The dark parts are called Urakauwe, which literally means monster water. Now, the Cherokee people from North America have a story about a dog that stole some cornmeal and got chased away. He ran north, spilling the cornmeal along the way, and thus the Milky Way, in the language of the Cherokee people, is called the way the dog ran away. And in Japan, the Milky Way is known as the River of Heaven, and there's a famous story from China the Japanese like to tell. There are these two deities in heaven, Orihime, the star Vega, and Hikoboshi, the star Altair. Now, Orihime was a weaver, and she'd weave beautiful fabric on the edge of the river of heaven every night. And so she was really sad and lonely sitting on the riverbanks, weaving all the time. So she was introduced to Hikoboshi, who was a cowherd. And then they fell in love and got married and promptly stopped doing their jobs. So there was no more beautiful fabric, and now there are cows wandering all over heaven. So the two lovers were immediately separated, and they were placed on opposite banks of the river of heaven, and they both cried so much about it that they're allowed to meet one day a year on the 7th day of the 7th month, when a bunch of magpies come in and make a bridge for them to cross. Anyway, the counterintuitive thing about the Milky Way is that it's not obvious. I mean, it's this big, cloudy, milky river thing, and we've been looking at it and telling stories about it since forever, but it represents a cosmological structure, an order of magnitude so large that we never even recognized it. The Milky Way is a galaxy. It's the galaxy we belong to. It's our galaxy, and in fact, the word galaxy comes from the Greek name for the Milky Way. The reason that it looks like a line of stars is because we're trying to look at it from the inside of it. We didn't even know what a galaxy was until like 100 years ago, when telescopes in astronomy had developed enough for us to recognize that the universe was full of these giant clusters of stars, containing bazillions of stars in orbit around their communal mass. The prettiest of galaxies are spiral galaxies. They're shapes like disks of stars, pancakes of stars, all rotating around the center, with prominent concentrations of bright stars lining up in spiral shapes, radiating from the center. And the Milky Way, this river of light and dark that crosses our night sky, we recognize that it too is a spiral galaxy. It contains something like 300 billion stars and something like 100,000 light years across. And we are kind of in the middle there. We're about 27,000 light years from the center. And that's a lot of numbers. So let's put this in human history terms, right? So mankind evolved in Africa and then spread out to all the other continents in the world. So the question is, imagine we have an observer sitting right in the middle of the galaxy, pointing their telescope right at Earth. What epoch would they see? I mean, light takes 1 year to travel a light year, so what would somebody in the middle of the galaxy see? Well, the center of the galaxy is so far away from us that a person looking at Earth through their telescope would see humankind learning to weave baskets. That's how long ago it would see. I mean, it's an incredible amount of distance. And if we had somebody on the far edge of the galaxy looking at us, the light they would see is so old that they would see Homo sapiens living in a time when the Sahara Desert was all wet and fertile. You know, an era so long ago that the end of this era was what pushed Homo sapiens from Africa to all the other continents. This is a crazy amount of time ago. So the Milky Way is huge. So huge, in fact, that all the other stars we can see in the night sky are actually part of the galaxy as well. But we can study our galaxy. We can study it by looking at all the other galaxies in the night sky. We can get a sense of how galaxies evolve, what happens to them in the long run, where they come from. And this can tell us about our own history. On this episode of the Titanium Physicist Podcast, we're talking about our home, the Milky Way galaxy. So, speaking of star-crossed lovers whose lives of love and regret are visible to everyone on Earth, today's guest has her own podcast called This Feels Terrible, where she and her comedian friends talk about their shameful and regretful memories of love. It's an extraordinarily brave show, and it's absolutely fantastic. She's a comedian and a writer, and she performs at the Upright Citizens Brigade Theater in Los Angeles. In fact, she has a show coming up on February 13th, a This Feels Terrible storytelling show. And she's also a regular on the Harmontown podcast. Welcome to the show, Erin McGathy.
Hello. Thank you for having me. Hi.
Hooray. Okay, so Erin, for you today, I've assembled two fantastic titanium physicists, very old friends who haven't been on the show in a cattle herder's age. Arise, Dr. Amanda Bauer. Dr. Amanda is in Sydney, Australia, at the Australian Astronomical Observatory. She got her PhD from the University of Texas at Austin, and she studies galaxy formation. She has a notable public figure on the internet where she blogs under the name Astropixie. Now arise, Dr. Rupinder Brar. Dr. Rupinder is one of the friendliest people I know. He's so good at making science fun that in 2010 he won TVO Lecturers of the Year's Award. He got his PhD from Queen's University, and he's currently a senior lecturer at the University of Ontario Institute of Technology. Okay, everybody, let's start talking about the Milky Way.
Aaron, so the way I like to think about the Milky Way galaxy is it's sort of like an ecosystem in a way. So like when we talk sort of on a granola crunchy level about everything on Earth, the plants, the mushrooms, the people, we like to think of it all as we all influence each other and they all influence us. We're all connected in a way. To me, that's what the galaxy is too. Every star, every black hole, every piece of matter, planet, whatever human alien you might find in this galaxy is all connected together. We have a shared history. And so I'm sure that a lot of people have heard this idea of us being made of star stuff. I think it's equally important to argue that we're made of galaxy stuff. Without having this structure, this factory, if you will, all of the raw ingredients that make us up wouldn't have coalesced into being able to make our solar system, our cell phones, and us at all.
All right, prove it.
Okay. So what is a galaxy, right? I mean, gravity is the most important ingredient when we talk about a galaxy. Like, what is holding us together? What is separating us from the next galaxy over? Essentially, all of the little pieces that I mentioned are gravitationally interacting. We're all orbiting the center of our galaxy. Just as we can easily imagine the planets, asteroids, comets orbiting the sun, us as a solar system, the whole sun, everything in our solar system, the Earth, we're all going around the center of our galaxy. And so are all of the other stars, so is the dust, the gas, the dark matter and all of the other exotic things that we're going to find in our galaxy. As far as what our role in that galaxy is, we're in a very interesting spot called the disk of the galaxy. I want you to imagine the galaxy if you can. Like, we all know what a spiral galaxy looks like. We've all seen a picture here or there. But to me, the important part of the galaxy that I want to talk about is a pancake.
All right.
You love pancakes,
Perfect.
right?
I do love pancakes.
Yeah. The best kind of pancakes, they're not those European skinny pancakes where there's nothing.
Are you talking about
a
crepe?
Yeah, no crepes. We're not talking about crepes. We're talking about like really good fat pancakes. Maybe flapjacks.
I know this isn't a breakfast podcast, but just in case you ever go to France, I think they'd be offended if you called their crepes skinny pancakes.
Skinny pancakes. You
really
might even be putting
for.
apples in that batter.
There's lots of baking soda. It's puffing up.
And so basically, we're not sitting still in this pancake. We are also orbiting the pancake too. And so us as a solar system, we're all moving together through this galaxy, and it's taking us about 200 million years to go around one time. Just like it takes the Earth 1 year to go around the sun a single time, it's going to take the solar system 200 million years. And it's a bit more interesting than that even. Instead of us just going around in a nice smooth circle, we're actually bobbing up and down. We're bobbing up and down in the skinny part of the pancake as we go around the center as well. Sort of like a carousel or a merry-go-round.
Do we go faster, or like as we get further out to places in the galaxy where it's thinner? Do we move faster?
So for the most part, we actually keep the same distance away from the centers. Our bobbing motion is happening sort of in the up and down direction if you were looking at the pancake edge on.
Okay, were we once in the middle of the merry-go-round and everything's spreading out, and that's why it's in that shape?
Probably not.
No.
Probably not. Oh, okay.
Okay, thinking about how the Milky Way actually formed, it would have formed from a big cloud of gas and dust, and that would have been kind of a big spherical thing. So bringing the food back into it, imagine if you're making a pizza crust. So you have to make the pizza dough, and you've got this big ball of dough. Mm-hmm. But you know how you kind of flatten it a little and then throw it up in the air and spin it a little bit, and it just flattens and gets thinner and thinner and thinner?
Yes.
So in terms of the Milky Way, when you've got that big cloud of dust that's a little bit more dense than the regions around it, it starts to collapse under the force of gravity. And this would have happened very early in the history of the universe, so very soon after the Big Bang. So as it started to collapse, it was sort of like that pizza dough ball that was spinning. The gas naturally starts to spin as it collapses under the force of gravity, and so it flattens out like the pizza crust. So it flattens and flattens and flattens, and then other sorts of crazy things happen. It isn't quite as simple as that pizza dough flattening out, but we end up flat, sort of like the pancake. But then there are little regions in that start to form into the spiral arms. So you get kind of density waves that move through, and that's where you get these tiny little clumps of gas that form new stars. So the
solar system
would have been formed in one of those clumps of stars that form in that gas that would have been in one of the spiral arms. And then we keep moving in that circle around the center of the Milky Way. We never quite move out or in. We stay about that distance, but we do move a little bit faster than the spiral arms. So we kind of catch up to different spiral arms over time. And our speed changes a little bit as we approach one of those spiral arms and go through it and come out on the forward end on the other side.
So the galaxy is shaped the way it is just because of the Big Bang, not because of like the current movement of the galaxy. It's all kind of stayed in the same spot.
The Milky Way formed in a pocket of gas, and the size of it is essentially because of what happened right after the Big Bang.
Okay.
But then how it collapsed and everything, that is sort of conservation of angular momentum and gravity and just the basic physics that we think we know. So that was all post-Big Bang stuff.
I think the thing that's confusing me is that it's almost like the opposite of the way that a ball of dough would spread out from spinning. The reason why it's doing what it's doing is because it was that shape and the gravity of that shape is...
So the Big Bang happens and the whole universe is like expanding everywhere, but it's not exactly completely smooth everywhere. There are tiny little clumps of regions all the way throughout the universe and that are a little bit more dense than other ones. So it's almost completely smooth, but not quite.
Okay.
So in each of those little regions that happen to be a little bit more dense, so there's billions of these all the way throughout the universe soon after the Big Bang, those little overdense regions, like that one little cloud, would have collapsed under its own little local gravity.
Okay.
And so that one little cloud would have then proceeded to form itself into a galaxy. And there are billions of those all the way throughout the universe soon after the Big Bang.
They're forming because they're collapsing? I don't understand the idea of something collapsing and then creating a galaxy.
That's a major field of study. So
If there were
first, what is collapsing is only gas. It's only like hydrogen.
Okay.
And then as that starts to collapse, it starts to get denser and denser and denser. And then you've got little clumps, then they start to form the first stars.
I see.
At the beginning, it was only a gas cloud, a big one.
Now I understand. Okay, I get it. I guess instead of thinking about gas collapsing in on itself, I was thinking about just like matter and stars and things.
Right. So soon after the Big Bang, there was only hydrogen, there were only particles. And then as soon as these first stars started to form, when that gas got dense enough for stars to form, then those things started to churn out all of our other elements like carbon and oxygen and all that stuff. And gradually over the next 13 billion years, they formed all of the constituents, the gas and the dust and the black holes and all that stuff that make up our galaxy.
We were getting to the question of why it forms a disk. The idea here is that before the structure of the Milky Way formed, there was just a whole bunch of gas in space, right? It's a little bit denser at one point than anywhere else, and then so all the gas says, hey, I'm being gravitationally pulled towards this slightly denser region. And then all of the gas in a great big ball ends up trying to collapse down on the center.
Gotcha. So it's the opposite of pizza dough.
We haven't jumped to the pizza dough stage yet. We're still taking the flour and adding the other stuff so that it can get to that pizza dough ball.
So in the pizza dough explanation, you start with a little ball and then you spin it so it's flat, right? What happened to this big ball of gas is that, so the reason the Earth doesn't fall into the sun is because it's in orbit. It's moving sideways relative to the pull of the sun. So the Earth feels a pull towards the center of the sun, but because it's moving sideways relative to that pull, it can manage to go in a circle around the sun instead of falling into the middle. Same thing with this big ball of collapsing gas. All the gas is going to end up collapsing down into the middle unless it's moving sideways relative to that pull. And this is just kind of there's some natural variation about where each glob of gas in this bigger ball of gas is moving. Some of it's moving left and right. And so, it sorts itself out over the course of its evolution so that the only gas that doesn't end up falling into the middle is the gas that was rotating in orbit. And so a big disk of orbiting gas forms, which is why we have this pancake shape, because it's pretty much all of the gas that wouldn't get sucked into the center because it would end up in orbit. When we think about galaxies, what we look at is stars, right? You imagine this big, vast ocean of stars. But the real story in galaxies is this dust and gas that's always collapsing down and is kind of in orbit around the middle. Because it's that dust and gas that is collapsing down and forming stars, right? And so the deal is, the star formation mirrors where the gas is slightly more dense. So the reason we see spiral arms in a galaxy with these nice kind of swirly spiral patterns is that there's kind of overconcentrations of dust as it orbits the center in these weird spiral shapes. There's a little bit denser dust there, and so that's where the stars form. There's a Canadian skating game called Crack the Whip where everybody's on skates. You hold hands and you start wheeling about the center, and then the person on the end gets thrown somewhere and breaks their neck, and then you can't play it anymore. Okay, so it looks, when we look at these spiral galaxies from above, it looks like the stars are kind of doing that. Like there's a big train of stars, but that's not quite what's actually happening. What's really happening is there's a long train of dust, a big overconcentration of dust that's spiral-shaped, and that's where the stars form.
Got it.
Okay.
Ben, if I can, do we want to talk a little bit about how we can tell what the Milky Way looks like? So I like to use this sort of twisted problem, if you can. We're inside this thing, right? And so to figure out what the shape of it is, how big the spiral arms are, I mean, we can see a very, very small fraction of the number of stars in our own galaxy. So the challenge to actually, first of all, understand that we're in a galaxy and then to actually be able to physically describe it is a crazy hard task that astronomers have been working on for about 100 or so years. And the analogy I like to put, if it doesn't freak anybody out here, imagine yourself kidnapped and you wake up in a room and you can't get out of that room, but you can look out at the window. And for some reason, your kidnappers left a phone in your room. You call the police and they're like, well, describe the house that you're in. That's essentially what the problem astronomers have is. We're confined to a small piece of this house and we can't even see the outside of it. But we do have one advantage in that we can see the houses in the neighborhood. Luckily, we're in a suburb built by a single builder, and we can describe the houses in our neighborhood. And essentially understanding that and, getting a sense of a little bit about, we have this many rooms or little tiny features help us understand overall what our own Milky Way galaxy looks like. Unlike our solar system where we've explored things, we haven't seen the Milky Way galaxy in any point of view other than being confined inside of it.
In this scenario, does our planet have enemies?
Do you mean are we supposed to be paying a ransom so that we can get out?
I mean, it's just such a funny analogy.
Yeah.
Because the first thing I think of when I think of being kidnapped is who did this. That has nothing to do with what you're...
It was clearly the Andromeda Galaxy did this.
Maybe our planet had a night where they went to a party where they were feeling self-destructive and had too much to drink and maybe met somebody and woke up in the morning and maybe they hear the noise of someone making pancakes, but they don't know where they are. They know they weren't kidnapped, but they know that they're in some sort of home, and then they call their friend and they describe where they are so they can get picked up.
I like that one. I'm going to use that with my 18-year-old students now.
Thank you.
What does this have to do with comparing the stars nearby us to...
galaxies nearby us?
Oh, we're looking at galaxies nearby us?
Yes. When you're looking out of the house and you're looking at the neighborhood around us, we're looking at other spiral galaxies like Andromeda, like distant M51 or something like that, because we want to know what our house looks like. And it helps us to get a picture. But, I mean, Amanda can speak more on exactly what we do inside our own galaxy to understand the big picture, how all these stars kind of fit together to give us an overall shape.
I thought that you meant that, we were placing ourselves within our galaxy. But you're just saying you're kidnapped and you look outside the house, you just want to know what the other houses look like. We're just seeing what everything else looks like to understand what we look like, not necessarily where we are, because we know where we are. Okay. All right. Got it. Maybe if you were moving into a new tract housing neighborhood and you were looking at the other, well, that doesn't make any sense.
Or if you're in a place where you don't have any mirrors, you've never seen yourself, and you're kind of looking at everybody else's face to say, oh, I have these eyes. That's what that person has. Oh, and I got this nose, too. That's what they have.
Yeah.
So trying to figure out your own structure by looking at everything else around you to see if you're similar or not.
Right.
The challenge with that is, say, in the southern hemisphere, you can look out and see the Milky Way streaming across the sky, and just next to it, you see these two tiny little galaxies called the Large and Small Magellanic Clouds. Full disclosure, astronomers are not very good at coming up with names. So these are entire galaxies that we can see, and they just kind of look like little smudgy white fuzzballs floating in the sky, and they're absolutely fantastic, but they're these little tiny galaxies that are stuck to the Milky Way. The Milky Way is the big one in this picture, and these two little ones are stuck to us, and they're actually orbiting around us, and eventually they're going to fall in and become part of the Milky Way. But right now they're separate, and we can see them, and they look absolutely nothing like the Milky Way. So that's a bit of a challenge to this, figure out what we look like by comparing ourselves to the other galaxies around us that we can see. So there are all sorts of tricky little ways that astronomers have come up with to try to figure out what we look like from the inside. The current count of spiral arms that we have is 4, which is actually a change from what we thought even up to a couple years ago. So we thought for a while we only had 2 spiral arms. But again, I can't jump in my space rocket and shoot out and have a look. So we have to guess by taking really detailed observations of as many stars in our galaxy as we can. And it turns out that a huge challenge in astronomy is still determining how far away things are. So I can look at a star and say, oh, well, there's 5 stars in a clump right over there, but it doesn't mean that they all actually live in the same physical space. It could mean that 2 are really far away and just bright, and 2 are kind of close by, but faint. But they look to our eyes that they're in the same place in the sky.
It's like when you take a photo of yourself high-fiving the Statue of Liberty.
That's funny. Or so people have taken on these huge surveys of different sections of the sky and tried to map out exactly how far away the stars are, and then seeing if physically they line up so that they could be in the positions of where there's a spiral arm or not. So there was a study that was going on for about 12 years, and it just came out last year. And based on the distribution of stars in our sky and figuring out how far away they actually are, they've mapped out that we have 4 spiral arms, and that our sun is just kind of at the edge of the Orion arm.
So from within our galaxy, what is it we see when we are looking at the quote-unquote Milky Way? Like, what is that one of the arms?
Oh, it's actually a whole huge chunk of the Milky Way that we see. So have you ever seen the Milky Way? Have you ever gone out and looked at it? Mm-hmm. Does it look like a smooth thing across the sky?
No.
Good answer.
It looks like it's all over the place. It looks like a cloud.
Yeah, it looks kind of patchy. It's not like
right.
a smooth stroke. There's some really bright glowing bits and there's some dark patches. And so that's us on the surface of the pancake, and you pull the pancake up to your eyes and you try to look through it. And you see the collection of all that stuff. It's like from the inside, we're looking through that whole edge of the pancake. And a lot of it is stars. We see the collective glow of all those stars in that direction, but some of it is dust. And the dust actually blocks the light of the stars behind it. So like on a cloudy day on Earth, you can't see your shadow because the clouds are blocking the sunlight. Mm-hmm. These dusty clouds in the galaxy are actually blocking the light from the stars. So some regions of that big Milky Road that you see across the sky are a bit darker, they're patchier, and that's just because there's more dust in that direction than in the other directions where you've got more of a glow and a bit of a brighter bit of the Milky Way.
So if there was no dust, it would look like there was a large, huge disk all the way around. There would be like a...
Really? That's crazy.
Yeah. It's blocking out the middle. And it's blocking out we can't see through it to what's behind the galaxy on the other side.
Not with our eyes. Yeah, we've had to invent a lot of other technology like infrared. So infrared actually can see the dust glow, and some other wavelengths, radio waves, for instance, can see through some of that dust. So we've come up with all these different sorts of eyes to allow us to see different components of the Milky Way and then map them out that way. So if you look in the infrared, it doesn't look like as many of the pretty little stars, but you see these big glowing gas clouds. It's pretty cool.
You know when there's a manhunt going on and they're trying to chase down some dude using one of the helicopters? Mm-hmm. And the person's hiding under a bunch of trees because he's like, no helicopter can see me when there's trees in the way. And they can't in visual, but then the helicopter has infrared sight. And, using this other wave band of light that passes through the leaves, they can see the person hiding under the tree.
Gotcha.
It's essentially that.
Do astronomers hate dust? Does that translate to your everyday lives, like when you're cleaning off surfaces and stuff?
Some really, really do hate it, but others actually study the dust itself. I think is very, very fascinating.
There's got to be a name for those astronomers, right? Like the dust bunnies, or that guy's a dust mite. Stay away from that guy. He just studies dust.
You can say it in a derogatory way, but I have nothing but respect for him because it's a difficult problem, and I really have no interest. I try to look at the places that are the least dusty. So I respect them a lot.
They're good people. Those dust bunnies.
Somebody's got to do it. Another method that astronomers have come up with to try to figure out where the stars in our galaxy have come from and also how old they are. Mm-hmm. So if you look at an individual object in the sky, it could be a star or a really distant galaxy or anything. Let's pick a star. If you take that starlight and you put it through a prism, you see its whole rainbow, right? Mm-hmm. And we enjoy the rainbows from our sun all the time. Other stars have their own little unique rainbows. So each star has its kind of rainbow fingerprint that tells you all about the chemistry of that particular star. So using this rainbow fingerprints of each individual star, you can tell how much hydrogen it has in them, how much helium, how much carbon, how much nitrogen, and the ratio of all these things tells you when it was formed. Because early on in the history of the galaxy, or early on, soon after the Big Bang, remember there's only hydrogen and maybe a little helium. So stars that were formed way back then would only have hydrogen and helium in them. But over time, more of these elements were formed, so stars that were born later would have more carbon and more nitrogen and more of the other elements. So we look at individual stars. We're trying right now to look at about 1 million stars within our galaxy to see what their chemical makeup is by looking at these rainbow fingerprints and then dating them to see how old they are and where they could have formed and if they would have moved over time. So that's one of the ways we age our Milky Way, is trying to figure out how old individual stars are.
Cool.
There's a fun story you can tell about deducing things about our galaxy. So Rupinder was talking about how we're like stuck in a house. We only have one perspective on this galaxy we live in. We can look at other galaxies all the way back to the start of galaxy formation. Have you ever heard of the Hubble Deep Field image?
Yes.
Right. So they took a camera and they pointed it at the darkest patch of the sky, the one with no stars in it, and they focused on this tiny little dot, and then they finally had an image. It was full of old galaxies. The deal is, as far as you can look in any direction, as long as there isn't dust in the way, you can see a galaxy, which is pretty cool. That's not my point. My point is that because we have this catalog of different galaxies, we can just see so many galaxies, you can get a sense of how they evolve. This big cloud of dust collapses down, and then over the course of its collapse, it'll form a disk, but then little pockets here and there of stars will form. And the deal with the star is, the reason stars glow is that in the center of stars, the hydrogen is fusing together to make heavier elements. And a really, really big star will start burning. We call it burning. It's not oxidizing like a fire, but the elements are turning into heavier elements, and in doing so, releasing energy. Which is why a star glows, right? And so a really heavy star will end up burning some really heavy materials and explode in a supernova. And that process, in essence, it starts out a big ball of hydrogen gas. That gas will collapse down into a star. The star will make a whole bunch of heavier elements like metals and weird lithium, whatever. And then it will explode in a supernova. In the process of exploding, it will release a bunch of these heavier elements back into the soup of gas that's, flowing down into the middle of the galaxy and doing its gassy stuff. And so the soup from which stars are made, the chemical composition of this soup is changing over time. As the lifetime of the galaxy goes on, the soup gets doped with heavier and heavier elements, and we can see that chemical composition change over the lifetime of the galaxy. So what you can do is you can look at clumps of stars, and a clump of star might form from the same big ball of gas. And so it'll have all the same chemical elements. And you can say, okay, that clump of star, it's moving in this particular way. It's located here. We knew that at one point in time there was a big ball of gas there and that it was moving in this way. And so if you kind of trace where these older stars are, you can get a sense of how the gas once moved through the galaxy as the galaxy was evolving. Does that make sense?
Yeah, no, I believe I am following you. Go on. Is our galaxy mapped out? How do directions work with a galaxy? Like, are there hemispheres? Is there?
Oh, good question. When you look across the night sky and you see the Milky Way, so we're looking through the disk. That's actually called, for a lot of astronomers like myself who study other galaxies, so we try to look out. Since that disk has such a concentration of dust, and it's really hard to see through it with optical, we actually call that the zone of avoidance.
That's
Almost
great.
all of the observations, like the Hubble Deep Field and these really deep images we've taken of the universe, are in the absolute opposite direction from that disk because we want to avoid all that dust as much as possible. So then, yeah, I guess it depends on what you're trying to study. If it's not really split into quadrants per se, like going from the center, it's more from our location. So we'll have often a certain angle, then we'll take that one section. But I think different kinds of studies call them slightly different things. The one I'm most familiar with is the zone of avoidance.
What made you want to study galaxies that weren't ours?
So I guess fundamentally it was my question the first time I saw the Milky Way with my eyes as to what it is, like why is it there? But then I learned pretty quick that it's really hard to answer those questions for our own Milky Way because we can't get any perspective on it. So I started to look at other galaxies because the pictures that we saw that we made with our telescopes were stunning. You could see all kinds of different sort of spiral arms and shapes among them. So I just started looking at more and more and more of those and realizing how different each galaxy really is, even though they all fit into certain general categories, like whether they have spiral arms or not. And ultimately, I think it is answering the question of how we got here and what the Milky Way is and what's going to happen to it over the next many billions of years. But I just kind of like the variation in all these different galaxies out there.
Yeah, I agree with Amanda. When we're in our own galaxy, it's really hard to see the forest from the trees. But if we look out at these faraway galaxies, we can almost treat them as a single system. Like all the cool things that are happening are all part of a single picture. But being too close to this one, inside of it, in fact, you're just kind of studying bits and pieces of it, and it's really hard to make it into a singular dynamic object, even though it is.
We were mentioning earlier that the galaxy has different constituents, right? It's made up of different stuff. There's stars. Stars behave in a particular way. They tend to just barrel through. They tend not to bounce off things because stars don't usually hit each other. Gas does hit each other, so if two big clouds of gas try to push through each other, they'll kind of bounce off each other, and you'll get another big cloud of gas doing its own thing. But there's also like dark matter, and we weren't sure how much dark matter there would be. And then there was the question of, what do black holes do? We know that there's a big black hole in the center of the Milky Way galaxy. We're not sure when that formed. And so these ideas would be really speculative, but we have computers. And so what we can do is we can tell a computer, we can say, okay, we know how all these things interact. We know how dark matter kind of flies around. We know how gas tries to pass through each other and bounces off each other. We know how stars interact and at what rate they form. Let's just simulate a galaxy. And so they set up computers and simulate galaxies, and then they compare to see what kind of galaxies they make, what kind of time frames galaxies form in, and then compare that to what we see observationally. And what we can do as a result is come up with a good sense, a modeling sense of how early or late the black hole in the center of the galaxy formed, whether it forms near the end of the galaxy formation or whether it forms very early on, what kind of a role the gravitation of the dark matter has on the gravitation of everything else. It turns out that it looks like black holes at the center of the galaxies form really, really early on. We know that it looks like the clumps of dark matter kind of clumps together in these, giant orbiting balls before any of the gas has time to collapse. So it looks like stage-wise, first it's the dark matter and the black hole, and then all the gas follows in and collapses down where the dark matter has collapsed in, and then it forms the disk and all the interesting things happen. So if you're in Rupinder's shed all kidnapped and you have nothing but time on your hands, you see how long it would take to build a house, and you get a sense of how houses are built. You're like, okay, we can't build the roof first.
Rupinder's shed is the name of my next novel. And novel.
Let's talk about the end state of the Milky Way galaxy. So the deal is that we can see a lot of different types of galaxies when we look out into the universe. And so we have a sense of the different stages of evolution in a galaxy. And so as a result, we understand what's going to happen to our own galaxy in the long run.
So I said before the large and small Magellanic Clouds are eventually going to fall into the Milky Way and become part of it. Well, we live in a little neighborhood called the Local Group. Thrilling name, is it not? And the Local Group is made of us. We're one of the big galaxies, and the Andromeda Galaxy is the other big, massive spiral galaxy. And then there's all these tiny little dwarf galaxies. The Andromeda and the Milky Way galaxy are barreling towards each other directly and will ultimately crash into each other and become one massive galaxy system, which hopefully has a name better than Milkomeda. That's
Wait, is that the working name?
That's kind of the working name. I keep saying
Milkomeda?
Milkomeda.
That's awful. I want to give science my friend's
Cannon
contact information. Yeah.
Please.
Luckily, we've got some time, right, Amanda? There's a bit of time to work out the name?
Got about 4 billion years to work on it. I'm going to try to push for androgyny way, because I think that's better. So after this collision happens, after about 6 billion years from now, we'll sort of settle into one big elliptical galaxy. We won't have our pancake shape anymore for a while. And then we will continue to just evolve. We have some other little dwarf galaxies that will crash into us. But at some point, dark energy is going to take over, and the expansion of the universe is going to be so rapid that we won't be able to accrete more galaxies. We'll be isolated in our own existence. And actually, the bit of the universe that we're able to see starts to shrink and shrink because of the finite speed of light, even as the universe expands and expands. So our supermassive black hole will get a little bit bigger. It'll start feeding on some of the material around it, and stars that exist in the galaxy will go through their evolution. We'll have a few more generations of new stars forming, but then we won't have enough gas to actually be able to form new stars. So stars will stop forming. Oh, I just looked this up for the show, actually. The age of the universe that we are in right now is called the stelliferous age. So the stellar age, the stelliferous.
What's the span of the stelliferous age?
So it will be now for about another trillion years.
Okay.
So once all the stars burn out, then we'll be left with a universe with just supermassive black holes who are left to their own evaporation through Hawking radiation. And that lasts for like trillions and trillions of years. And it's not entirely sure what is going to exist after that. Probably just an age where there's the leftover particles from the black hole evaporation floating around. It's going to be very cold and very dark. And that brings us to the end of our story. Yay!
So how do we know that when we collide with Andromeda that it won't make an elliptical galaxy?
All of the simulations that we've done and images we've taken of other galaxies that are in the process of colliding, because we're coming head on and because of the angles that we're at and because of the other smaller dwarf galaxies involved, there's probably no chance that we're going to redeem any of our disky features. So it's just going to be a really chaotic billion years or so, and all of the mass is going to be shoved down into the center. So we're going to build a very big, what's called a bulge at the center, and just lose all of our disky shape. And we actually don't know what is exactly going to happen to our sun. So as the Milky Way comes, all of our constellations are going to completely redesign themselves because the stars will be changing their positions relative to us. And it's likely that our sun will probably get moved towards the outside of this final galaxy system, but it's really hard to predict that, even with the sophisticated models that we have.
One thing that won't happen, though, is that our solar system's not going to hit another solar system. Our stars aren't going to collide with one in Andromeda. The funny thing is, even though there are 300 billion stars in each of these galaxies, they're so far spread apart that no two stars may even collide during this interaction.
Yeah, that's always fascinating.
Yeah, that's crazy. Right? I mean, really, as far as like what it's going to look like from Earth is we're going to have like double the number of stars in the sky.
So, Erin, to put the question I asked Amanda a second ago in context, there are kind of two different broad classes of galaxies we see when we look out. There are nice spiral-shaped ones where everything's in a disk, and you get that nice spiral army-looking thing. And there are other ones that just look like it's like a swarm of V's. There's just a swarm of stars all orbiting the center. And those ones are called elliptical galaxies. And it looks like the way elliptical galaxies form is that two smaller galaxies once upon a time collided. And then in the process of colliding, a whole bunch of gas ended up getting smushed into the black hole at the center of one of them. And then doing that released a whole bunch of radiation. There's something called a quasar when matter falls into a black hole. I'm not sure if you saw the Interstellar movie.
I have not.
Well, there's these fantastic pictures of like black holes where there's like a swirling like disk of gas around it. I'm not sure if you've seen the photographs from the movie. So the deal is that matter as it falls into the black hole gets really, really hot and really, really bright. And so if you pour a galaxy worth of dust into one of these supermassive black holes, what it'll do is it'll shine so brightly, the light off it will come off so hot that it will blow away and ionize all of the gas and dust in the galaxies. And because there's no more gas and dust, new stars can't form. And the reason we see our galaxy being disk-shaped, like I said, it's the story of what's happened to the dust. The stars form where the dust is, right? And so what's happened is all this dust and gas in our galaxy has formed in kind of a disk shape, and so all these new generations of stars have formed following this disk shape. So that's why our galaxy is kind of disk shaped. So what happens in these galactic collisions is, because all the dust and gas blows away and ionizes, you don't get any new stars. And so nothing's forming a disk, and so none of the stars are growing in a disk, and so all you end up with is this big swarm of old stars. And so my question to Amanda is, how do we know that that's not going to happen to the Milky Way when it collides with Andromeda? And I guess the answer is they did the simulations, and it looks like it's not going to happen to ours this particular time.
Well, why wouldn't there be an active phase? I guess it just depends on how much gas actually gets fed down into that very central region of the galaxy, because it only gets active if that gas gets really, really, really close to it.
Well, that was wonderful. Thank you, Amanda. Thank you, Rupinder. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Rupinder, you get a blueberry pancake. And Amanda, you get an apple pancake.
Yum, yum.
Wonderful. I'd like to thank my guest, Erin McGathy. Thank you, Erin, for coming on.
Thank you for having me.
Everybody should be listening to her show, This Feels Terrible, and it's about relationships and stuff, and it's pretty cathartic.
Thank you.
All right, everybody, it's announcement time. So, first, I hope you're enjoying the Question Barn episodes. If you'd like us to answer your questions, send your questies to TIE Fighter, TIPHYTER, at titaniumphysics.com. Second, good news, everyone. Our Patreon campaign is doing very well. We've reached our second fundraising goal, so now we're transcribing the first and a past episode. And so I've got a backlog of transcription for the transcription guy to do. I'm very happy with it. We're uploading them to the websites as he makes them in PDF format. If you got any other ideas about what to do with them, drop me a line. On that note, I'd like to remind you that we're now accepting donations. We'd be grateful to receive your support, of course, and you can make a one-time donation using PayPal through our website, or you can start up an automatic donation on the Patreon website. This particular episode of the Titanium Physicist podcast has been sponsored by a collection of generous people. First, I'd like to thank the generosity of a man named Dennis H., a man named Joshua, Mr. Bobby Richter, a Mr. Aaron Fisher, and a Mr. John Keys. I'd also like to thank Ryan Close, Peter Clipsham, Mr. Robert Halpin, Elizabeth Teresa, Mr. Paul C., and a Mr. Brian Newell, Mr. Adam K., Thomas Charret, and Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Josh, and Steve. Thanks Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. Thanks to Brent Knopp for remastering our intro. I appreciate the help. So that's it for Ti-Fi this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Bracula Media Network. Keep listening after the end music this time. There's a fantastic bit of discussion following it. Yeah, it's really great. Okay, so the intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. So, good day, my friends, and until next time, remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
And so imagine this pancake. It's fat in the middle. If you look at it sort of face on, it looks like this beautiful round circle. And let's say we put some syrup on that's
Okay,
sort of
so-
the shape of spiral arms. Go ahead.
I'm harping on this crepe thing, but if you took two crepes and put fruit in the middle, maybe that would look more. I mean, it's
I like that.
It's isn't it scientifically impossible to have a pancake that's thick at the middle? But you're saying you would put more while it was cooking? I won't understand the galaxy at all unless you clarify this apple.
No, I disagree. I've had plenty of pancakes that are like fat in the middle and then they thin out to the edges.
Really?
Those are the best ones.
Are you cooking on a convex pan?
I'm not actually cooking it, but my mother-in-law is making these exact pancakes, and they are stuffed. I don't know if that helps. Maybe
they are stuffed. Okay.
There are blueberries and apples sort of in the middle that helps make them fat in the center.
Interesting. Do you know why she put the fruit in the middle of the pancake?
I don't know that she does. Maybe it like spreads out. Like, so what if you like took like a spoonful of batter and you like chunked it in the middle of the griddle or something? Right. And then the batter sort of spreads out naturally, but the fruit will remain where it's sort of plopped down.
Okay, I don't believe in space anymore.
Rupinder, your explanation was so confusing that she doesn't believe in space anymore. Does the reason our galaxy is pancake-shaped make more sense now?
Yes, I do understand. I also think that someone's mother-in-law is making pancakes incorrectly.
Oh, Rupinder.
They're the most delicious pancakes in the entire world.
I'm sure they're the best. I mean, she's doing them wrong. She should call them something else. I do.
I think the thing about these pancakes is there's a viscosity issue. I think the viscosity of the batter she's using is less thick than the ones you're used to using.
Absolutely.
And so her pancakes, when she'll glob on some dough, the dough,
Yep.
the fruit all stays in the center, but then the dough is so runny it spreads out wider than the center.
Right.
But pancake dough should be viscous. Erin's right, Rupinder. You got to have words with your mother-in-law.
Over the course of, and I don't know how long all of you have been career scientists, but like, have there been any like earth-shattering, maybe life-changing like discoveries that have happened? Like, because I'm assuming you guys are all relatively young. Has there been anything that is?
I'm 21 actually.
Are you? Professor, I mean, I know that you guys aren't in your 60s. So, like, has there been any like big career discovery or like a thing that's kind of like changed the game?
Yeah, it happens every 5 years. I'd say something really.
That's so cool.
Oh yeah.
So then, why is anybody so like arrogant about anything they believe ever? If everything changes every 5 years?
Very good question.
I feel like a lot of the changes are, I mentioned that there are too many theories and not enough goats in the trees pruning off the bad theories.
Right.
I feel like a lot of the big revelations that happen aren't new theories that crop up, but instead somebody finally sticks a goat in the tree and it chomps off. And so there's been wonderful theoretical discoveries over the course of my life. Like they discovered the Higgs boson a couple of years ago.
Yeah. But also we're sort of expecting things to change. Like I know that there are things that I don't know. So for instance, the discovery of planets around other stars.
Yeah.
There were so many years where I had to listen to talks where people were saying, okay, we're still looking, we haven't found any yet, but this is my technique and this is how sensitive I am and this is, we're almost there, but I haven't found any. And then all of a sudden, I don't know, 10 years ago, even maybe less than that, the techniques started to get better and better. They were refining and building better telescopes, and so you're able to see that like small little flicker a little bit more than you could the year before. And we started to find these planets. So it's kind of like we knew it was coming and we just had to get better at how we were looking. And so all of a sudden now there's an explosion. There are thousands of planets around other stars, and it's like every day there's more that are being announced. But it took a long time to get to that point.
And how do they announce the stars? Is it like a ball?
Does everybody dress up in tuxedos and then they open an envelope?
Well, I was just imagining the stars.
Probably, but now it's kind of a
I mean, is there an email? Is there a like oh, there's this new star. And then who the stars are named after the person who discovers them, I'm assuming.
No.
Oh.
They all have names like 112AB Giselle K, right?
Oh,
I guess that astronomers are not very creative in naming things, and mostly stars are named after their either the survey that discovers them or the location that they are in the sky, so they're like coordinates. And then the planets that would be around that star are that star's name A, that star's name B.
Doesn't that feel like that's a whole betrayal of the culture of looking at stars, isn't it? Like from ancient people coming up with these great stories, we're just giving them numbers
because there's a lot of them. There are billions and billions and billions and billions of stars.
I happen to know a professional namer, which sounds like a joke, but I'm friends with like the premier person who names things. Like she mostly names cars and a ton of other things, but like I'd say like more like luxury products, like cars and things. She was a poet. Her name is, and this is not her real name, unsurprisingly. It's Cannon Wing. She did. She named herself because that's her job, and that's her whole calling.
There's something kind of deific about that, isn't there?
Oh, absolutely. Of course.
First, you're so good at naming that first you name yourself and then you name everything else.
Yeah, I don't know. Her and I are just acquaintances because I frankly am terrified of her because she's someone who names everything, which is...
Yeah, you might get a new name.
She renamed herself Cannon. That's how I know her. But I feel like these stars should have a name. I have a question that I'm sure is probably pretty tired for Amanda.
Mm-hmm.
What is it like? Like, what's the culture of being a female astronomer? I have no idea how many female astronomers there are. Is there a certain light that's cast?
The longer you're in the field, the fewer women there are. So when I did my PhD, there were half female PhD students, half male. And that's about, it's maybe 40 to 50% women at the PhD level, maybe 40%, pretty close to worldwide. I mean, there's changes in that. But then it becomes more difficult to stay in the field, or there are just kind of more forces acting against you to make things a bit more difficult as a woman in the field.
What are some of those things?
There's kind of the obvious ones about if you want to start a family, if you want to take some time off. Different countries give you different abilities to take maternity leave or give you some leeway when you want to come back to the job. There's just a general, like if most of the people who I work for are men, then there's not a whole lot of role models. There's not a whole lot of people to kind of look up to that have gone through this sort of same things. There are definitely instances of sexism and bullying and harassment and things like that around, as much as we don't want to admit it. And a lot of it is kind of accepted culture. And when it does happen, if it's sexual harassment or just harassment, it's harder to make the decision that you're going to make an official complaint against it, because most universities will have a whole bit of paperwork and formalism that you have to go through in order to make that complaint. But that faculty member,
if your peers or like the people that are above you are doing that, it's not like you're in the business of not doing what you want to do.
It's a huge power play. That's the reason most of them can get away with it. And me, I experienced it, for instance, as a PhD student. I just wanted to get on with my work. Like, I just wanted to study. I wanted to get myself away from this person as much as possible, but I didn't know how to confront him. I tried to sort of go up the ranks, but everything got smoldered, and he never really got reprimanded for it. And little instances of this happening over and over and over really start to burden you, despite the fact that you just want to get on with doing your research. Yeah. And I'm not saying that every woman experiences those things, but most of the ones that I know do. And after a while, I think a lot of people just kind of get sick of dealing with those things over and over. And there might not even be one blatant instance of it, but just gradually it builds up, and it's so exhausting.
Yeah. So, are you friends with other female astronomers, or has everybody built up this armor that makes them? I'm projecting, but like with the.
I do know a lot of female astronomers. I do know some who have never experienced any sort of issue at all. I know some who have dropped out of the field because of it.
Really?
Yeah.
That's such a shame. Just for
the way they were treated by some blatant harassment And then if they take it up to a senior level, the peers of that person who is doing the harassing tend to defend the harasser. Because that person's senior, they've been around for a long time. You don't want to shake the boat. Why would you want to ruin the career of this person who's been here? As opposed to thinking of the person who's been harassed. Like, what happens to that person's career?
Yeah. Rupinder and Benjamin, have you witnessed that? What is your experience with the women in astronomy? And I have no idea how many.
Yeah, I mean, there's just not enough of them as far as I'm concerned. I do everything I can at the undergraduate level. This is where I interact mostly with students. I don't take grad students and that, and so I'm purposeful in my mentoring of undergraduate students and trying to get them excited and engaged and doing research and that kind of thing, and hopefully leading to them picking this as their career. But I'd like to ask Amanda, do you find that our generation is better, or do you see the harassment coming from all ages?
It definitely tends to be a power issue in that it comes from senior people to junior people. That's the typical thing. The challenge is going to be, are my generation and my peers willing to step up when they see something or when they're told that something's happening? One problem is if there's a senior person who is, say, harassing me, I have to find I'll give you an example of an incident. I had to find someone who is a senior person, a peer of that harasser, and go to that person and say, this has happened and I'm uncomfortable and I'm not sure what to do about it. That person of mine who interacts, like those two seniors, those peers interact constantly, and my safety person in this instance had never witnessed anything or had never been aware or even suspected that this person would do it. And once I said something, all of these other stories came out. Wow. So there are ways that you see it, but you just want to ignore it. You don't want to get involved. And what needs to happen is more people need to step up and say, I'm an advocate. I'm on your side if you need help, or just kind of go and step in a conversation, or don't let somebody get away with being an asshole because they always have been an asshole. That's not okay.
Yeah.
Yeah.
And getting each other's backs. I think the hardest thing is dealing with people with the harasser who has been yes-anded and given a pass by so many people over and over again, and no one wants to shake the boat or make their life about the harassment they're receiving.
Yeah, and maybe sometimes, I'm going to be honest, sometimes they don't even know that they're doing it, but they've gotten away with it so much for so long that they've kind of kept pushing and pushing and pushing, and until somebody that they respect says, you're making this person feel really uncomfortable by that behavior, they're never going to change.
I mean, it's kind of good news that it's people that are older, but I understand that if the culture isn't changing, that's just going to continue on, and people are going to be grandfathered into that.
Yep,
system.
That's the challenge. So it needs to be talked about, and it needs to be acknowledged, and it needs to be recognized when it's happening. And it can't just be the women who deal with the burden and support each other. We need men.
Yeah, for sure.
Yeah. Oh no, absolutely, yeah.
I think some of the other things that I've tried to do as well is give examples even in the course of lectures of historical injustices to women as sort of, check out this ridiculous situation. Here's the story of Jocelyn Bell, or here's the story of Annie Jump Cannon, and these great women of astronomy who basically did this really, really important work, but for a considerable amount of time, they didn't get any credit because they were women. And then the countless others who didn't get a shot to do that because they were women.
Yep.
Hopefully that helps.
As a woman pursuing something that's traditionally male, I think the most powerful thing from a teacher is the expectation that your offering is going to be just as scrutinized as anybody else, and there's going to be, everyone's going to be recognized a certain way, and there's not going to be we got the girl is going to do the thing. Not that that's anything that you would do ever.
Just read a quote from Bauer today that was along the lines of, a man will say something and it'll be heard the first time he says it, and you could say the same thing as a woman, but you have to say it 5 times before you're actually heard. And
Yeah.
I do feel that sometimes. But then the interpretation is that I'm a bit of a bitch because I keep pressing this same point.
No, I know. I mean, it's going to be it's super fucking unfair, and it's going to be unfair for a while. It is. I just read this thing this last week, which is the 5th study that I've read about the same exact thing, which is about women in the workplace complaining about. We're not even complaining about things that happen, but just like going over women's reviews versus men's reviews. And unequivocally across the board, if a woman's in a leadership position, she's a bad person and she's doing something wrong and she's a bitch. And that's just the way that it is.
And I think it's not just in the sciences. It's when you look at the fraction of CEOs that are women, or you look in political positions, a lot of these things are kind of the boys' network. And you have to be pretty tough to stick in for a long time to make it through. But we need people in senior positions to act as mentors and to act as advocates for diversity in these roles, which needs to happen worldwide.